Hi, good morning and welcome to the ZP Developer Zone. So we do this webinar every Thursday at 8 a.m. London time, and we do it primarily to kind of answer technical questions that have come in from the week. So we'll essentially jump straight into it. So the first thing we will do is I always bring up this slide, but I'll be very quick with it. This week we are going to talk about Industry 4.0, and we are going to talk about monitoring in the process industries. And because I'm not going to spend a lot of time on the electrochemistry, I'm going to sort of assume some sort of knowledge of electrochemistry. But there is something called the ZP Academy. ZP Academy has some resources on it. I'll highlight which resources to look at. Now, as part of sort of ZP's support of the community, every week we do a live streaming webinar. This is it, but we also do other webinars as well. We do have collaborations. We've got a very good collaboration going on in India at the moment, especially with Technando. Obviously, we do offer jobs through the ZP website. There is a ZP Developer Zone, and there are workshops, and I'll just discuss workshops as well. So I will go quick. The reason I go quick is you'll understand that I'm actually doing a workshop today. So just so you know, this is a workshop today. It's obviously a little late to attend. It is in-person workshop, but we'll be doing that today, and it's starting sort of 9:30 a.m. Central European time. So that's why I'm going a bit quick today. And this is also why we've started the webinar a little bit quicker than normal. Or earlier than normal. Also, just know that we've also got a webinar being organized in India as well through our great partners in India, Technando. And also just to say that we are doing a live workshop in San Diego on the 10th of November. So this is also something that's happening, and people are welcome to attend. Now, I did say that we're going to assume some sort of level of understanding of electrochemistry or electroanalytical chemistry. I will be using examples of voltammetry today, and the only reason I sort of have this little animation running is really just to kind of transition to here and say, look, we do have something called the ZP Academy. The ZP Academy, academy.zimmerpeacock.com. It does have a couple of free courses on it. So if some of the techniques like voltammetry that I'm obviously going through today are not super familiar to you, then you can also have a look on the Academy course as well, or the Academy courses, and they are free. Now, today I want to sort of focus in on the process industries. Now, at Zimmer Peacock, we are ISO 13485, so we have an excellent quality system around the development and manufacture of electrochemical biosensors. And I think electrochemistry is part of a science called electroanalytical chemistry, and it has a really big role to play in Industry 4.0 and Lab 4.0. Now, first of all, what is Industry 4.0? Industry 4.0 is a sort of, and by the way, there is also a sort of an equivalent Lab 4.0. It's essentially what's considered the fourth industrial revolution. In this particular revolution, you will have equipment that is collecting data. That data then is able to be turned into information. That information can then guide other equipment. So, there's something called, in the pharmaceutical industry, they're very interested in PAT, process, I think it's process analyticals or something like that. But they do PATs, and PAT is this kind of online continuous monitoring. And this has been a concept that's been around for 20 years. But it's only really a technology that's, I strongly believe, is only really going to be able to come about now, because the vendor that makes the sensor is not necessarily the vendor that makes a pump or a stirrer. So the whole idea of you have equipment that's maybe from different vendors and historically has not been able to communicate. Really, I think a lot of developers of technologies now are sort of buying into this concept of Industry 4.0, where it's much more open architecture, and that's definitely something that ZP is interested in as well. Again, I'm talking fast because there is a workshop starting in approximately 40 minutes, and I'm giving it, so I'm doing this webinar quickly. So as part of Industry 4.0, there is a protocol out there called OPC and Open Platform Communication Unified Architecture. It's a bit of a mouthful, but when I talk about making sensors for the process industries, at ZP, we're very much buying into this OPC architecture. So at Zimmer & Peacock, we already have this architecture built into the sort of the fabric or the DNA of the company. We make electrodes. Electrodes are the sort of starting point of any electroanalytical system. We have the electronics. These are fully functional potentiostats, but we can also deliver the data in such a way that a non-electrochemist can also use the data. What's really key to our whole kind of, we call it sensor to API, or you can also think of it as sensor to OPC UA, is that we actually can then make apps. You know, we tend to work on Android because I think it's just lower cost, to be honest with you, for the end users. We tend to work on apps. So we're able to make electronics connect to a smart device. It could just be an Android pad, or it could be an actual Android phone, but it really just, the nice thing about the use of Android devices is that they do give you easy access to the internet, because as long as you get them onto the Wi-Fi, then they can have connectivity. So at ZP, we have a stack of technologies: electrodes, electronics, and the ability to make apps. By the way, I will talk specifically in a minute about inline monitoring of processes in, for example, organic synthesis. But at the moment, I'm just describing the architecture, and then I have to go back and talk about the actual sensing part itself. So we have electrodes, electronics, apps, and this is really important. We have a proprietary database system called Julie. It's been 8 years. We've been working on it for 8 years so far, so it's got to a good level of maturity. This database can receive electrochemical data. This is really important because the one thing about electrochemistry is not everyone can interpret what they're actually looking at. But once you move the data to the cloud, it means you can provide either online support using sort of AI interpretation of people's data, or you can actually use other people to help interpret data. And that's something that we do at ZP as well, is when a client is using our system, because their data is going to the cloud, we can actually, they can grant us access, we can log in, we can have a good look at it and help them out with it. Now we convert that data into things like concentration. Like here I put ppm, parts per million. We don't mind if it's molar, milligrams per deciliter. It's just a calibration factor essentially. So at Zimmer & Peacock, we're very much bought into the Industry 4.0. Industry 4.0 has a subset of it called Lab 4.0. Lab 4.0 is really about interoperability, that different devices in the lab can essentially talk to one another. And for us, even with electronic lab books, you need to get all this data to the cloud, and it's intrinsic in our sort of core stack of technologies at ZP. It means we can do things like pass and fail. Is this reaction within bounds? Is this reaction outside of bounds? And then we can pass that data on using what's called an API call. Now, specifically this week, we are discussing the idea of following a chemical reaction in a continuous process. So, for those who are didn't know or may not know, there's generally two ways of doing a chemical process: batch process and a flow process. In a batch process, you have a big pot. Everything goes into the pot. You stir it, you heat it. The reaction takes place, and at the end of it, when you think there's got sufficient conversion, you essentially stop the reaction. Now in flow, I think, which is much more elegant, you have, and I'll describe it in a minute, sort of two or more streams coming together. It could be one stream. You have a reaction zone, and then you hope that the products are flowing out to the end of the reaction zone. But I will sort of explain that a little bit more now. The thing is, in both flow and batch, there's not always good inline monitoring, or there's not good online process monitoring. So let me describe a scenario here. So the scenario is, I have this organic molecule. I have part of this I've made up, but the voltammetry is not. But I'm sort of just doing a thought experiment. So the thought experiment is this. At the moment, people tend to use electrochemical techniques in flow processes, and they use conductivity. Conductivity is something you get for free when you do proper electroanalytical chemistry. I'll say it again. It's something you get for free when you do proper electroanalytical chemistry, but proper electroanalytical chemistry gives you so much more data. So I have this scenario where I've got a methylated kind of phenol here. I will just, I know not everyone's an organic chemist, but I will describe that. And I'm going to demethylate it using a hydrogen and a heterogeneous catalyst. And essentially I sort of remove, there's a methyl group here, CH3, and I just replace it with a proton or hydrogen atom. Fairly simple. Now, with electrochemistry, or rather the process that I'm imagining is this, that you've got a packed column. So this is a sort of stainless steel tube in which you've got a heterogeneous catalyst. You've packed it with something that's sort of proprietary to yourself, and you have two flow streams in. You have maybe a liquid stream here, and either this could be liquid or gas, it doesn't super matter, but you have two flow streams. Essentially, one of them is the starting material, and maybe the other one is a sort of reagent, and these two things come together, and they pass and they flow over this catalytic bed, and they essentially flow out as product here. I think the first way, if you want to do inline monitoring of, for example, a reaction like this, is actually I think the simplest way to do it is to have an inline flow sensor cell here. So it's not the world's best term, but it's an inline and it's a flow cell and it's got a sensor in it, and I'll talk about that in a minute. So if I was to sort of go back a bit and then we go forward, Industry 4.0 is kind of here. As part of Industry 4.0, you really want to have kind of process control and process monitoring where actually that kind of data is going to the cloud in real time, and maybe then you're able to sort of take some action upon that data. Now, I think flow chemistry, people are doing a very good job in terms of the synthesis part of it, but they're not always necessarily got inline monitoring of it. But I think electroanalytical chemistry really offers a great tool for doing inline monitoring of chemical reactions. So I now need to try and expand on the sort of last box on this, which is this inline flow sensor cell. So here's my molecule, which is this kind of methylated phenol. So I'm going to, now if I did the voltammogram of this molecule, excuse the cough, if I recorded that using proper electroanalytical chemistry, I would get essentially, it's called a voltammogram, but I would call it a spectrum. I get very distinct peaks. This is an oxidation, this is a reduction, but I have a fingerprint for this molecule. It's in some ways more powerful than techniques that people tend to use, which is like HPLC. Because in this example, with HPLC, you get one peak. In this voltammogram here, I get two peaks. One of them is because the molecule is oxidizable, and one of them because the molecule is reducible. So I have more of a fingerprint, I would say, than even HPLC can necessarily produce. Now, this is the product of my reaction. Now, the product of this reaction, when it's partially formed, I have an extra peak here. So it's quite distinct. So what I'm describing here is that I have a starting material that if I demethylate it, the product has a very distinct peak from the original starting material. So I can actually see the reaction product and the starting materials, both essentially. Now, it is a voltammogram, but I like to use the word spectrum sometimes because people are familiar with spectrums. If I told them this was an absorption spectroscopy, they would be like, oh, yeah, I understand it. This is really the electrochemical equivalent of it. So electrochemistry is kind of very powerful because you can actually have this electrode in line recording multiple CVs, and then you can watch the transition of these cyclic voltammograms with time and watch the, once the conditions are correct, then essentially the product should diminish, sorry, the product should enhance, those signals should enhance, and the starting materials should disappear. And by the way, you can look at this spectrum, you can actually get conductivity out of it. Conductivity is just the measurement of sort of electronic resistance, but with full electroanalytical techniques, you have that resistance or conductivity anyway, and you get proper peaks, which are their position tells you what the molecule is, and their height tells you how much the molecule is in there. So it's really quite, I think, quite powerful. Just to say that at ZP, if we are validating one of our electrochemical sensors for a chemical reaction, we do have HPLC, so we can show an equivalence, that when you're trying to produce white papers or test reports, etc., we do have HPLC, so it's not like we don't actually have the methodology that is familiar to, for example, people in the pharmaceutical industry. So we do have that. It's 8 o'clock now, so if you're joining just now and you're thinking, well, this guy seems to be rather into this, it's because I had to start the webinar a little bit early this morning because I have some workshops, but just rewind and you can watch it. So how to implement inline monitoring in flow processes. So what I'm meaning is how to implement this kind of flow sensor cell that I've indicated here. So the way I would implement it, first of all, you need an electrode system. This is one of our ZP electrodes. This one is the one I sort of super recommend because actually it is very chemically resistant. This has been used in DMF, THF, acetonitrile. It doesn't have any problems with organic solvents. So we have an electrode. That's great. Now you can use an electrode like this. You could actually just do what I would almost call spot testing, where you take a sample of the reaction, put it onto the sensing end of this, and we can run a voltammogram that way. But that's spot testing. You're kind of doing near process monitoring. What the questioner is asking is, how can I do inline monitoring? And in principle, quite easily. So I will jump in a little bit more on this and say, implementing this at ZP, we do have a whole bunch of flow cells. I will have some links to those flow cells. Now, the first thing to say is that anyone in the chemical industry that works with organic solvents will look at the materials of construction and say, oh, there's a lot of plastics here. Obviously, the tubing is things like PTFE, polytetrafluoroethylene, or ethene maybe, ethylene. So it's inert, but I do want to show you that we do have an equivalent. So first of all, this does look low pressure. And what I'm thinking is, to make a high pressure system, it takes more engineering. But of course, when you look at flow systems, they often essentially sort of drip out into a collection vessel. Well, it's not that hard to actually have them not flowing out into a collection vessel, but actually have them flowing through an extra flow cell in which the electrode is placed. And I'll explain that a little bit now. So we have these flow cells. You can put the electrode into them. You can clamp down this cell on top of it. You have these kind of little sort of thread adapters, and then we can put PTFE tube in and PTFE tube out. So you essentially just put an extra flow cell in the system. The reason I'm doing it this way is because if you want to prove out a principle, then you try to get, use off-the-shelf components just to prove it out. Once you've proven it, you can actually then get a bit more sophisticated in actually sort of building it. The only reason I show that is that's a LEMO connector, and it connects to our laboratory instruments. Just to say about the materials of construction, we do have a glass version where everything wetted is either glass or PTFE. Again, these are low pressure systems. So low pressure systems, I mean, once you're at kind of more like atmospheric type conditions, then we can deal with it. Otherwise, yeah, it will leak. But we do have these flow cells, and it's good to start low pressure rather than high pressure. And I think even a lot of, as I said it before, flow systems, in the end, they often, are collected at atmospheric. So it's just taking the tube that was collection and actually putting it into this flow cell and just flowing over the top of it. We obviously do have the instruments to run this. We can just plug the flow cell into here. When I say the flow cell has electrical connections, and electrical connections have to plug into here. It's probably worth saying a device like this fits in the palm of my hand. What is so beautiful about electrochemistry? What is so beautiful about electrochemistry is the electronics have been getting smaller and smaller now for years. Unlike photo systems, I mean, people, if you have an infrared system, they're big and bulky and quite high powered. Why is that? Because it's hard to generate photons and it's hard to count photons. Photons have no mass, no charge. Electrochemistry is all about electrons. Electrons are great. They have mass and charge. They're easy to measure because it's called current. And at ZP, we have been working in flow systems and valves and switching valves and pumps for quite a while, but it's always in the medical space, and it's always at low pressure, where I realize that in obviously the process industry, sometimes people need much higher pressure systems. So if I was to summarize it, at Zimmer Peacock, we have a whole stack of technologies around electrodes, and those electrodes are resistant to organic solvents. We have a whole stack of flow cells, which are, some of them are all the wetted parts of PTFE and glass, but they do work at low pressure, not high pressure. So you do have to come out of a pressure system, be atmospheric, and then you can flow into our system. So we do have those flow cells, and obviously we also do have the instruments as well. And amusingly, we also have HPLC for that sort of comparison validation. And I know that actually also what we have at ZP is a sort of an Industry 4.0, a Lab 4.0 strategy, where actually all the data is continuously collected and actually sent to the cloud. And from the cloud, then you can have a kind of an OPC UA strategy, open protocol communication, united architecture strategy, where actually the data then can go into other people's systems or control other people's systems. So I'm going to stop it and wrap it up there. I'm sorry I had to speak very fast this morning. Like I say, I'm actually giving a webinar I'm actually giving a live workshop in approximately 23 minutes. So I do have to jump into that. But if you've got any questions at Zimmer Peacock, don't hesitate to reach out to us. And we essentially appreciate